A Boeing 777-300ER takes off with 321,000 pounds of jet fuel. Not a single pound of it sits in the fuselage. Every ounce, 47,890 gallons of kerosene, is inside the wings. And nobody put it there for convenience. The popular YouTube answer is, wings are empty space, the fuel had to go somewhere. That answer is wrong. The fuel in those wings is doing 7 different jobs. We'll meet them in order. Fuel in the wings isn't storage, it's structure. To understand why, we need to talk about a 1949 jet, a Concorde at twice the speed of sound, and 230 people who died on a clear summer evening over Long Island. Look inside the wing of any modern airliner and you'll find the same architecture. 2 outer tanks, 1 in each wingtip, 2 inner tanks between the engines and the body, and a center wing tank, sitting in the box where the wings meet the fuselage. On the 777, those 5 tanks together hold 47,890 gallons. On the A380, 81,890, over 250 metric tons. The biggest A380 even hides a 6th tank inside the horizontal stabilizer at the tail. The fuselage carries people. The wings carry fuel. The question is, why? Here is what happens when a 777 leaves the runway. The wings have to lift roughly 775,000 pounds of airplane into the sky. To do it, they generate millions of pounds of upward force. Most of that force pushes on the outer half of the wing, far from the body. Now picture the wing as a long, thin lever. One end is bolted to the fuselage, the other end is free. Lift pushes the free end up. The fuselage pulls the bolted end down. And the metal in between has to absorb every pound of bending force trying to fold the wing in half. Aerospace engineers call this the wing root bending moment. It is the single largest structural load on any airliner. To survive it, the wing spar would have to be enormously thick, enormously heavy. In 1946, a British engineer named Ronald Bishop stared at that exact problem. He had just been handed the impossible job of designing the world's first commercial jet, and he found a solution nobody before him had ever needed. On July 27, 1949, the de Havilland Comet 1 took off from Hatfield Aerodrome, north of London. Inside its wings, sealed between the spars, sat 7,257 gallons of kerosene. Bishop hadn't put it there to save space. He'd put it there to save the wing, because mass at the wingtip pulls down. Gravity acts on the fuel exactly opposite to the lift, acting on the wing skin above it. The two forces cancel. The bending moment trying to fold the wing collapses. The spar no longer has to carry the full load alone. The technical name is wing bending relief, and the structural saving is enormous. Roughly a quarter of the wing's structural weight is removed because the fuel inside is doing the work the metal would otherwise have to do. The result is counterintuitive. The fuel makes the wing lighter, drain the tanks, and the wing is heavier than when they're full. Bishop's team had not chosen to put fuel in the wings. The math had forced them to, and every commercial jet built since 1949 has copied them. Bishop's insight didn't just shave weight off the Comet, it changed how every wing flexes. On March 28, 2010, Boeing engineers at Everett, Washington, ran the most violent test in the 787 Dreamliner's certification campaign. The static airframe, ZY-997, was bolted to the floor of a hangar. Hydraulic jacks attached to the wings began pulling upward. The wings were loaded to 150% of the most extreme force the airplane would ever encounter in flight, and they flexed upward. Slowly, deliberately, the tips rose, until they had moved approximately 25 feet above their resting position. The wings did not break. They were never supposed to. What that test revealed is something every passenger has felt without naming. In normal cruise, the 787's wingtips flex up and down by several feet, smoothing turbulence by absorbing it. The wing breathes, and how much it flexes depends on how much fuel is inside. A full tank pulls the tip down. An empty tank lets it ride higher. The wing is not a rigid plank. It is a tuned suspension, and the fuel is the tuning weight. Here is a small fact about the fuel in those wings. It is also a refrigerator. Inside every commercial jet, the integrated drive generator, the box that turns the engine spin into electricity, runs hot. So hot, it would seize within minutes without cooling. So does the engine oil. So does the hydraulic fluid on wide bodies. The solution was simple. Route the hot fluids through heat exchangers that pass them next to the cold fuel on its way to the engine. The fuel absorbs the heat, the oil cools, the fuel arrives at the combustor slightly warmer, which actually helps it burn. It's so effective that on the F-35 fighter, the fuel is the primary thermal reservoir for the entire aircraft's avionics. In 2014, the U.S. Air Force at Luke Air Force Base in Arizona had to start painting their fuel trucks white because fuel cooked by the desert sun couldn't absorb enough heat to let the jets start. Job 3, propellant. Job 4, refrigerator. The most dramatic job the fuel does is one almost nobody alive has ever flown to witness. When Concorde accelerated through the sound barrier, something strange happened to the air over its delta wing. The aerodynamic center of lift, which had been sitting comfortably mid-wing in subsonic flight, slid aftward by approximately 5 to 6 feet. Without correction, the nose would have pitched up uncontrollably. The plane would have become unflyable. Concorde's engineers built 13 fuel tanks into the airframe, several of them dedicated to trim alone. During the transonic acceleration, the flight engineer pumped roughly 10 tons of fuel rearward and into a tank in the tail. The center of mass shifted aft to follow the center of lift. The airplane stayed level. It was the flight engineer's full-time job to monitor the CG indicator and adjust the pump rate by hand. Fly too slowly to move the fuel aft, and you stalled. Move it too fast, and the airplane tumbled. When Concorde decelerated back through Mach 1, the whole process ran in reverse. Fuel pumped forward. Wings stayed flyable. The fuel was acting as a moving counterweight, sliding aft to compensate for the laws of supersonic flight. Not burned, just relocated. Concorde retired in 2003. Its fuel as counterweight trick did not. The Airbus A380, the largest commercial airliner ever built, has the same idea built into its bones. Hidden inside the horizontal stabilizer at the tail is a trim tank, a sealed fuel cell whose only purpose is balance. During cruise, as the wing tanks burn off fuel, the center of gravity drifts forward. The autopilot would normally trim the tail elevator up to compensate, which creates drag, which burns more fuel. The A380's fuel system fights that by quietly pumping fuel aft into the trim tank, sliding the center of gravity back to the optimal cruise position. The elevator sits almost neutral. Trim drag drops. Fuel burn drops with it. There's no flight engineer. There's no manual lever. The system runs itself every cruise on every A380 in the world. The fuel has gone from Bishop's wing bender to a silent, automated counterweight in the tail. Every gift the fuel gives comes with a hidden bill. On July 17, 1996, at 8:18 p.m. Eastern Time, TWA Flight 800 lifted off from JFK bound for Paris. A Boeing 747-131, registration N93119, 230 souls on board. 12 minutes later, climbing through 13,800 feet over the Atlantic south of Long Island, the airplane disintegrated in midair. There were no survivors. Investigators from the FBI suspected a bomb. Eyewitnesses saw a streak of light heading toward the plane and reported a missile. The FBI spent 16 months and recovered 97% of the aircraft from the seabed. Investigators found no missile fragments, no high explosive residue patterns, no warhead damage. On November 18, 1997, FBI Assistant Director James Kallstrom announced there was no evidence of a criminal act. The streak in the sky was burning fuel. The NTSB's final report, Aircraft Accident Report AAR-00-03, pinpointed the cause. The center wing fuel tank had been nearly empty. The 747 doesn't always burn from it first. But empty doesn't mean empty. Inside that tank, jet fuel vapor sat mixed with air, heated by the air conditioning packs running directly beneath it. Somewhere in the wiring of the fuel quantity indication system, a short circuit pushed excess voltage into the tank. The vapor ignited. The tank exploded. The fuel that had been holding the wing together had killed everyone on the airplane. The NTSB had buried inside its report a finding more uncomfortable than the wiring fault. For 40 years, aviation had been relying on a single safety barrier. Don't let anything ignite the fuel vapor. The vapor itself, flammable, present, sitting inside every wing, had been treated as acceptable. TWA 800 proved it wasn't. The FAA's response unfolded over a decade. In 2001, Special Federal Aviation Regulation 88, SFAR 88, required design holders to review the fuel tank system of every transport airplane in U.S. service. In 2008, the reduction of fuel tank flammability rule went further. Every U.S. commercial jet had to install either an ignition mitigation system or, more commonly, an onboard inert gas generating system. OH-BIGS. OH-BIGS takes air, strips out the oxygen, and pumps nitrogen into the empty space above the fuel. Below roughly 10% oxygen by volume, jet fuel vapor cannot burn. The mixture is dead. By 2008, every U.S. commercial jet was quietly breathing nitrogen into its center wing tank, a system that exists because aviation finally stopped trusting one barrier. The engineering didn't stop with nitrogen. When Boeing built the 787 Dreamliner with carbon fiber composite wings, a new problem appeared. Composite skin doesn't conduct electricity the way aluminum does. A lightning strike on a metal wing dissipates harmlessly across the skin to ground. A lightning strike on a composite wing concentrates current at the strike point, millimeters above a tank holding tens of thousands of pounds of flammable kerosene. Boeing's fix was 3 independent systems, all defending the same fuel. First, expanded copper foil embedded in the composite skin gives the lightning current a path to follow. Second, insulating polymer caps on every fuel tank fastener prevent an internal arc from ever reaching the fuel. Third, the OH-BIGS nitrogen system sits inside the tank as the last line of defense. 3 systems, layered together, protecting the same kerosene that was holding the wing together. The fuel had become more than structure. It was now a hazard the entire wing was engineered to contain, a hazard the wing also could not fly without. So count the jobs. 1. It fills the empty wing. 2. It kills the wing root bending moment that would otherwise crack the spar. 3. It powers the engines. 4. It cools the hydraulic system, the IDG, and the engine oil. 5. It shifts the center of gravity, slowly on a 777, dynamically on Concorde, automatically on an A380. 6. It killed 230 people in 1996. 7. It now flies surrounded by nitrogen, copper mesh, and insulating caps because of them. You cannot remove the fuel without redesigning the wing. You cannot redesign the wing without changing the airplane. Fuel in the wings isn't storage, it's structure. A 1949 design decision by Ronald Bishop, made because the math left him no choice, became the structural law every jet builder has followed for the next 77 years. So go back to the ramp at JFK, the 777, sitting in golden light. 321,000 pounds of kerosene flowing into the wings. The pilot inside the cockpit, running through a checklist. He doesn't think about Ronald Bishop. He doesn't think about Concorde. He doesn't think about TWA 800. He doesn't have to. Because every gallon being pumped into those tanks is already doing 6 jobs before he pushes the throttles forward. The fuel in the fuselage is what people see. The fuel in the wings is what holds the airplane together. Fuel in the wings isn't storage, it's structure. If you want to see why airliners almost never fly above 40,000 feet and what happens to the wings up there, that breakdown is right here.